Welcome to this lecture about rigid body simulation in Blender. We're going to start straight in and we're going to make a plane, and what is already important here is the physics tab for the rigid body simulation. That means if we go to the physics properties right here, we have all the simulation types that exist, and I will come to all the other simulations on later lessons, but at the moment we're only interested in the rigid body option in this lecture. The rigid body physics are applied when several hard, so non-deforming objects collide with one another. This means that if I have this plane here and I take a cube, for example, and I move this cube up, and now I want this cube to fall down on the plane, then I can do that with rigid body physics. For this, I will select my plane and set it to rigid body, and we're going to do the same to the cube. And now they're both activated in the rigid body simulation. Now, if I let the animation play now, both of them will simply fall down. Why is that? Because both are on active mode. In the rigid body simulation, there's a distinction between active and passive. Now, if I select my plane and switch that to passive and run our simulation now, you can see that our cube collides with our plane and it all works wonderfully. Now, I can also rotate the cube, for example, and then you can see that the cube comes down first, and then it would realistically fall over into place as a cube should. The surface response, which means how much friction or bounciness I want, can be set here as well, and that makes a huge difference, especially on this plane. Now you can see it's all very bouncy now, but we also have the sensitivity here, and we can set a collision margin. If we set this margin very high, then we can see that it collides before we even touch the plane, so those are the most important elements to set up. Now I can add multiple active objects, and if I add a monkey here, for example, now I'm going to go up here, and then we set rigid body active 2, and then I'll let the simulation play out, and you can see that the cube and the monkey actually collide with each other as well. So that means if we duplicate the monkey a few times, be sure that it's not interconnecting, and we drop it all at once, then they will collide with each other and roll around here and so on. But as you can see from the monkey, it's not exactly a clean render. First of all, of course, we set the collision margin far too high on our plane, so let's figure that out first and then let the whole thing run again. But second, you can see that our monkey doesn't look quite the way it should. It's almost like the geometry is not used for our calculation. So how can we change that? Well, the standard collision shape is the so-called convex hull. And that's not what I see in the picture here, but some kind of geometry superimposed on our object. And that's sort of geometry you would have here with a shrink wrap modifier, so to speak, if you applied it. And this works as sort of a simplified version of your geometry. If you really want your geometry, you can also switch it to the mesh right here. And our simulation is a bit slower, but you can see that it is way more precise. For example, objects are also colliding with the ears of the monkey, etc., etc. Now, if I may give you a quick example here, we have a torus, and the collision shape is set to convex hull. Now, we do the same with a cube. We make a cube up here, and let's take it both up now, push it up, and see what happens. You can see that there's some geometry put around our torus, and that means you can see that our cube collided with an invisible wall at the top, which is not supposed to be there. If we really want our cube to accurately respond to the torus, then we put the torus into the mesh mode, and then we have exactly what we want. It goes right through the middle. Now, there's other collision shapes, for example, a sphere, capsule, cylinder. This is all fairly self-explanatory, but you can then make the most important settings for your rigid body simulations right here. With all this information, we can, for example, make an animation of rolling a die or rolling multiple dice. Question is, how can we make it fall from an angle as opposed to just from the top? Well, there's an option here, and it's called the animated option. We can give our object a bit of momentum, so to speak, and we can ultimately do that with this. Now, I'm going to show you that very briefly. This means that we want our cube to come in here from the left. Okay, well, we'll now activate animated, which means we want to set a keyframe here for the location and the rotation, and then set a keyframe at 10 for the location, and then the rotation again, of course, and we just spin our cube a little bit like this. Now, what I want to do is let the animation play until frame 9, but stop at frame 10. So we make a keyframe at frame 9, then we go to keyframe 10, and it should then be deactivated. So first we uncheck the box, and then we press I to make a new keyframe. This is very important because then the keyframe will actually register you unchecking the box. Now, once we've done that, you can see that we now have a pretty good dice animation. It is rolling a bit too far now, but that has something to do with the friction. We can set that up very briefly. Now we go to surface response, and let's make the friction very high. And we can also set up the dimensions and the mass here, so maybe give this thing a mass of 10 kilograms. Yeah, that looks way better. Also, we can adjust the bounciness, and we could just make our plane a little bigger, so now we have this simulation right here. Right, come on, stay on the plane, stay on the plane, stay on the plane. Yes, it stayed on the plane. Perfect. Now we can also simulate a cube with this animated option. We take our cube and we make an array of our cube, very simple, with an array modifier. We do the factor x to 1.5, and then we simply press apply. Then we do the array modifier 1.5 on the y-axis and make it a count higher here again, and we do apply again. Very nice. And then we apply that again to a new array modifier, but this time on the z-axis with a factor of 1.5, and we make the count a bit higher, and there we go. We get ourselves a cube made out of cubes. Now we can go into the edit mode and press P and say separate by loose parts, and then these whole cubes will be created on the top right here. Now we would have to click on each of these cubes individually and add this physics simulation here. However, we can also just go here on our base cube, so to speak, and then leave the shape on convex hull, and then the friction, bounciness, and everything fits. And our measure is 1 kilo. We'll just have to try it out now. And now we go into edit mode, we press P, and we do by loose parts again, and now each of these individual cubes has to be in this simulation. And with that, we can now simulate everything everything together. But it looks a bit weird, doesn't it? Why is that? That is because the origin of all dice is still here where the origin of this die is. And that is the only cube that is now physically accurately simulated is this cube right here. Everything else is just kind of doing its own thing. That means we can now select all of these cubes here. We do right click and we say set origin to the center of mass, volume. And now we have all our origins in the center of all these cubes. And now we would have all these cubes on top of each other. Then we could also take a ball here, for example, and animate that. That means we go here, we say type animate, we do I for location and rotation. We can also just say location, it doesn't really matter. And it should fly into this angle or maybe even higher. We press I for location and rotation, go to frame 19. Then we remove the tick box, we set the keyframe, and then we make another keyframe, and then we have the following simulation. It's a bit underwhelming, isn't it? I maybe need to put up the mass. Let's put it to 20 kilos. And now our box tower is completely destroyed! And it's definitely nice that it works like this. This is the kind of stuff you can do with rigid body simulation, and those are the things you can do with rigid body physics. One thing I want to show you is rigid body world. You can create a collection, so to speak, and everything that happens in that collection has the same rigid body physics. That means I can now create a new collection, and then I can say rigid body here, and then say collection rigid body here. And now I can put various rigid body objects in this collection, and now you can also see that our simulation no longer works. We basically told Blender to put everything in a collection, but that is not the rigid body collection, so we have to select everything, all our cubes, our sphere, and our plane, and put that in the rigid body collection, and then you can see that everything works again. And we can also set up the simulation speed, for example. That's pretty cool too. But of course we have to adjust this with the keyframe so that the whole thing works again, and then we practically have the same simulation as before, but just a bit faster. And then we can also set the substeps per frame and the solver iterations and stuff like that. Now, when I put it down, you can see in any case that this will be significantly more imprecise. And now we have exactly this weird jittering effect. We basically have a few more settings options that we can just do in rigid body physics to fix this. That is it for rigid body physics right now. The upcoming lecture is going to be about cloth simulation. I am already looking forward to that. It's going to be complicated and a bit longer, but I'm excited. I hope you are looking forward to this as well. If you find this video cool, please give me 5 stars. I will be very happy. And we'll see each other in the next lecture when it comes to cloth simulation. See you then.